let me illustrate the usefulness of the notion of absolute convergence by this series. So notice that cosine k here in the numerator changes sign, so it can be both positive and negative, and it does that in a very unpredictable manner. So this is very much unlike the alternating series, in which the behavior of signs is very predictable. It's plus, minus, and so on. Here, on the other hand, we have very unpredictable behavior of the signs of cosine k. In fact, its magnitude is quite unpredictable as well. And so it's not clear how to reduce this series to any of the convergence tests that we have seen. So the integral test, the comparison tests, they will only apply for a series which has non-negative terms, but this is not the case for this series. So what one should do instead here is apply absolute values to the terms of this series. So if we consider of these as AKs, then the series of absolute values of AKs that we want to consider next. So we want to look at the series of absolute values of AKs. Right, so what is this series? This is the sum k from 1 to infinity, absolute value of cosine k over absolute value of k squared, but k squared is of course non-negative, so we're going to simply write k squared in the denominator. Now this series has non-negative terms. In particular, we can apply all the convergence tests that we discussed previously to it. Notice that the absolute value of cosine k in the numerator is never bigger than 1, right? So if you look at this expression here, it's at most 1. It's less than or equal than 1. So to use that, we're going to invoke the comparison test. We're going to say, well, because the numerator is at most 1, and this is a series with non-negative terms, we can estimate it from above by replacing the absolute value of cosine with 1. And so as a result, we have this nice and simple series, which is convergent as a p series, p equals 2. So what is the conclusion? That the series of absolute values is convergent by an application of the comparison test. And so what this implies about the original series is that it is absolutely convergent. And so the original series is absolutely convergent. And this is great because this means we do not need to be concerned about the specific behavior of sine of cosine k. We do not particularly care if it's positive or negative, because we have seen that once we apply absolute value to every term, that series converges, giving us absolute convergence of the original series, giving us in turn its convergence in the usual sense. And so the original series is then convergent. And so we can note that this completes the problem. So we have tested the series for convergence by passing it to the series of absolute values of its terms. We have shown that that series is convergent, which implies convergence of the original series by this theorem here. So that is a typical example of when absolute convergence needs to be applied. Now, in the next videos, we will discuss convergence tests, which are specifically targeting absolute convergence. And so they can only give the answer as absolute convergence of a certain series or its divergence. So let's discuss that now.